Hello everyone, welcome everyone to this session on analog electronics. Analog is fun, analog is design, so let's get into some beautiful fun and entertainment with analog design questions. So we are going to solve some very beautiful, very concept oriented, crisp concept oriented questions that have come in GATE and other competitive examinations in the topic of analog electronics. Let's get started. Okay, let's look at the instructions for playing the quiz before we actually play the quiz. So it's going to be all the quiz questions are going to be multiple choice questions or NAT type of questions. The link given here shows this is the link. Kindly I request all of you to log into this link bit.ly/tga085e. Okay, this is the link for playing the quiz. Okay, so how to play the quiz? As I told you, all the questions are going to be multiple choice questions or numeric aptitude based questions. So for numeric aptitude based questions, you just key in the value. For the multiple choice questions, you just select. Okay, there are no negative points, so you can play without any fear. And the number of points per question and the time given per question will be displayed along with the question. And tougher questions will have more points. And the interesting part is this: you answer the question fast, there's a reward for it. Higher the score, faster you answer, higher the score. Okay, there's a reward for getting to the answer first. Okay, so with all these things, let's get started. All the best. Let's get started. So let's wait for a few players to join. Just we will wait for a minute or so. Okay, we have students joining in. Let's see. Welcome Tushar. Let's see who else is joining. Okay, let's see. I'm just inviting the folks in the YouTube live also. Let's see. Let's wait for one more minute. So, okay. Okay, let's get started. Okay, here comes the first question. Okay. Consider the circuit shown in the figure. Both M1 and M2 are MOSFETs working in saturation region. Okay, M1 and M2 are MOSFETs working in saturation region. Their small signal parameters are given. They're asking you what is the value of Z0. So R1 is the internal resistance, R2 is the internal resistance of M2. So what would be this? Z0. Cool. Cool. There has been one correct answer because many people get confused. There's a cascode connection. Many people get confused. Let's see. Okay. Let's go further. Let's look at the leaderboard. Wow, Reshmi, cool. So Tushar, you can still catch up. Let's see. Here comes the second question. M1, M2, M3, M4 are MOS transistors in saturation region. GM1, GM2, GM3, GM4 are their transconductances respectively. The internal resistance of MOS is very large. Neglecting the channel length modulation, the mid-band voltage gain V0 by Vi is dash. What is the value of the mid-band voltage gain? Let's see. These questions are really very interesting and very thought provoking. Let's see. Okay. Oh, no one has given the correct answer, so it's really a tricky question. Let's see. So Rashmi continues the lead. Tushar, you can still catch up. Let's see. Here comes the third question. Okay. Op amps are ideal if I is 0 amperes. What is the value of R? The op amps are ideal if I is 0 ampere. What is the value of R? So think about this. We have two op amps. Op amps are given to be ideal. So think about the properties of ideal op amps. What all properties of ideal op amps can be of use? These type of questions are very, very famous in GATE and very common in GATE. So let's see. Last 15 seconds almost remaining. Let's see. Okay, so 9 is the correct answer. R is 9 kilo ohms. Nobody gave the correct answer. So let's see. Here comes the fourth question. Okay, this is also another interesting question. What is the type of feedback in this circuit? It is a current sensing, current mixing, current sensing, voltage mixing, voltage sensing, current mixing, voltage sensing, voltage mixing. What is happening? What is the correct type of feedback in this circuit? So look at the transistor from the small signal point of view. So understand what is the input here, what is the output here. So these are really very important. Okay, let's see. Okay, the correct answer is current sensing, voltage mixing. Nobody has given the correct answer. So let's see. The final question is coming up. Okay, VB on is 0.7 volt, VC sat is 0.7 volt, beta is very large. Switch S is closed at time t equal to closed for long time and opened at t equal to 0 seconds. BJT will exit active region after dash milliseconds. So here the switch S was kept closed for long time and then opened. VB on is 0.7 volt, VC sat is 0.7 volt and beta is given to be very large. It's a very beautiful question. You need to understand what is happening here. And the question is, after how much time the BJT will exit active region. So you should know what is the property for active region, what is the property for saturation, what is the property for cutoff, all these points very clearly. So this question covers multiple concepts in one shot. It's a very, very beautiful question. Okay. Okay, nobody gave the correct answer. The correct answer is 1 millisecond. So I think Reshmi is the winner. Congrats, Reshmi. Congrats. Well done. Let's look at the solutions. Solutions are more important. Let me pull up the solutions and share the page. 1 second. So here comes the solutions. So let's look at the question and the solution. So the question was like this. First question, we had two MOSFETs M1 and M2 connected like this. And M1 had a base to, sorry, the gate to be grounded. M2 gate was supplied with Vi. And they were asking Z0. The question says M1, M2 has a GM1, GM2, R1, R2. Correct. So this is the transconductance. And this is the resistance. And they are saying that both M1 and M2 are MOSFETs operating in saturation. Correct. So this is what is shown to you is this is the signal picture. Okay. The circuit shown is the signal picture, because they have already told the MOSFETs are working in saturation region. That means there is some biasing circuit and other circuits which is making M1 and M2 work in the saturation region, which is not shown. So they have shown only the signal picture of the circuit, small signal picture of the circuit, and they're asking you what is Z0. So let us draw the equivalent circuit. So this is the equivalent circuit of a MOSFET. So this is M1, right? So we have the drain, source, gate, drain, source, gate. Correct. Let us draw both the transistors. We have two transistors. This is GM1, VGS1, R1. We have GM2, VGS2, R2. Correct. And this is your VGS2. This is your VGS1. Now what is happening? The gate of M1 is grounded. The gate of M1 is grounded. So the gate of M1 is grounded. This is your M1. This is your M2. The gate of M1 is grounded. Correct. Then this is where you are looking in and finding the impedance. The source of M1 and drain of M2 are connected. Source of M1 and drain are, this is the gate, drain, source. Correct. Gate, drain, source. So source of M1 and drain of M2 are connected. So I'm making this connection. This is at ground. So they are asking you the impedance, what is that not looking into this port, correct? And when I'm, so effectively we are finding output impedance. Whenever you are finding output impedance, what we should do, short the input if it is voltage, open the input if it is current. So here the input is a voltage, so I need to short this. This also I need to short. So now let us look at it. Observe VGS2 equal to 0 volt because the source is at ground. The source is at ground and you grounded the gate because you are calculating the output impedance. So the input needs to be shorted. So the input is at ground, Vi is at gate is at ground, source is at ground. So what will happen? VGS becomes 0 for this one. So now what will happen? This implies what? Let us redraw the circuit. Now VGS2 is 0, that means this becomes 0. If this becomes 0, there is the current source is 0. That means effectively the current source is open circuited. So we have just R2 bottom, in the bottom. In the top we have, this is grounded because the gate of the M1 is grounded. GM1, VGS1, R1. This is where you are looking in and this is grounded. So the looking in impedance here is Z0 and this is grounded. And this voltage is your VGS1. Correct. Now we are asked to find, so effectively we are asked to calculate the RTH of this circuit. Correct. Correct. This effectively we are finding the Thevenin's impedance of this circuit. That's what it means. Correct. Correct. Because you are looking in from here and you are finding the impedance. So what we can do, I can assume an independent current source. So effectively the circuit looks like this. Let me redraw that. GM1, VGS1, R1, R2. Now I'm going to put this is where I need to find the impedance, Z0, and this is your VGS1. This is grounded. So I'm going to put a dependent, I am going to put an independent current source. And Z0 equal to V developed divided by I test. So this is your V developed. So I'm putting a current source and I'm measuring what is the voltage developed across the current source. So the voltage by current will give you the resistance. This is simple Ohm's law, nothing more than that. Now look at the beauty. Irrespective of how that I test is going to get divided between this and this, whatever may be, the entire I test will flow here through R2. So the drop here is I test into R2. Now what is the drop here? The drop here is the drop between this terminal and ground. So this terminal and ground is VGS1 like this. So therefore VGS1 is minus I test into R2. So therefore GM VGS1 equal to minus GM1 I test R2. Now minus current flowing down is same as plus current flowing up, correct? So this current is going effectively in this because this current is assumed to flow down and the current flowing down is a negative current. That means the current flowing up will be a positive current. So effectively this current is plus GM1 I test into R2. And from here I test current is coming. So by Kirchhoff's current law, how much current will flow through R1? IR1 is nothing but GM1 into I test into R2 plus I test, which implies voltage drop across R1 is GM2 I test R2 plus I test the whole into R1. That is the voltage drop here. Correct. This is VR1. Now, what is V developed? Ultimately, I know what is I test because this is a test source. I am only assuming it. I need to find V developed. If I find V developed, I am done. Z naught is found. So, what is V developed? V developed is VR1 plus VR2. Correct. VR1 plus VR2 is V test. So, what is VR1? VR1 is R1 into GM2. I am going to bring I test common outside. So, GM2 R2 plus 1 times I test plus I test into R2. VR2 is I test into R2. I test into R2 is your V developed. Therefore, Z naught equal to V developed by I test, which is R1 plus R2 plus GM2 R2 times R1. Correct? So please look at this. This is very, very important. So it's very, very important to understand. So many people, they will think that these two transistors are in series. The options are very cunningly given. Many people will think that M1 and M2 are in series. So the impedance of M1 is R1, the impedance of M2 is R2. So the impedance will get added up. That's why R1 plus R2 is given. Somebody may think it is R1 parallel R2 also. That's why R1 plus R2, R1 parallel R2 and all are given in the options. But in reality, the impedance is greater than R1 plus R2. It is GM2 R2 times R1. So this is called cascoding, and cascoding boosts output impedance. Kindly note this point. Cascoding, what is cascoding? Cascoding is a common source followed by a common gate amplifier with MOSFET. I can do the same thing with BJT. If with BJT, it will be a common emitter followed by a common base amplifier. If I try to do this with BJT, and cascoding is a technique to boost the output impedance. Okay. Okay. Let's look at the next question. The next question goes like this. V naught by Vi equal to what? Okay, what is given to you? This is your, let me look at the transistor numbering correctly. Yeah, M1, M2, M3, M4. M1, M2, M3, M4, and their transconductances are respectively GM1, GM2, GM3, GM4. Okay. Now, and also it's told neglect channel length modulation, and they have told R of the transistor is very large. So first let us understand this circuit piece by piece. Okay. So now they are asking you to find V naught by Vi, right? So let me look into the circuit in part by part. So first let me look at the input. Let me call this voltage as Vx. So how the circuit is looking, the input circuit is looking like this, correct? This is your M1, this is your M2, this is Vi, this is the VDD, ground, and V0. No, sorry, Vx. Now, what is Vx by V0? First, let us calculate this. So, whenever we have an amplifier, the gain is nothing but transconductance into output impedance. Now, what is the impedance looking into the, so whenever you have a MOSFET, kindly remember, whenever you have a MOSFET, the impedance looking into the source is 1 by Gm. The impedance looking into the drain will be R. The impedance looking into the gate will be infinity. And if you have a diode connected connection like this, the impedance looking into this terminal will be 1 by Gm. These are known facts. These are the facts we already know based on our understanding of MOSFET. Now, what is the impedance looking from here? The impedance looking here is 1 by Gm1 because the impedance looking into the source. What will be the impedance looking into the drain? It will be R. So what will be the what and the transconductance? This is the amplifier. So the transconductance of the amplifier will be Gm2. So the gain here will be minus Gm2 because from gate to so drain there will be 180-degree phase shift into output impedance. Output impedance is what? This R and 1 by Gm will be parallel because VDD is also like ground for me in the small signal picture. So see, from this node you have a path to ground like this, you have a path to ground like this. This is also a path to ground, this is also a path to ground. That means effectively in the signal picture these two transistors are parallel. So what you will get? 1 by Gm1 parallel to R. But it is clearly given that R of the transistor is very, very large. That means 1 by Gm1 parallel R is approximately minus Gm2 divided by Gm1 only. Okay, this is V0 by Vx. Sorry, Vx by Vi. Now let us look at the second stage. The second stage looks like this. Here you have a diode connected transistor and here Vx is getting applied. And this is V0. And this is VDD. Now again look from here. In the signal picture, VDD is like ground for signal. Because why? Because in small signal, we are looking at what is changing in the circuit. Whatever is not changing is ground. So VDD is constant, so it's as good as ground. Ground is constant, so ground is as good as ground. Correct. So we are looking at the small signal picture. In small signal picture, we are looking at what are changing in the circuit only. So now what is V0 by Vx? V0 by Vx is again transconductance into output impedance. So this is your M3, which is having Gm3 transconductance. This is M4, which has a transconductance of Gm4. And we have a diode connected transistor and we are looking here. So the impedance looking into here. So the transconductance, this is the amplifier, the transconductance will be Gm4 into the impedance looking into the source. Sorry, impedance looking into the drain with a diode connection will be 1 by Gm. So it will be 1 by Gm3 parallel to R of the bottom transistor. So this is going to be minus Gm4 divided by Gm3. This is Vx, V0 by Vx. Therefore, V0 by Vi is equal to V0 by Vx into Vx by Vi, which is minus Gm4 by Gm3 into minus Gm2 divided by Gm1. Minus gets cancelled away. So this is the overall answer. Gm4, Gm2 divided by Gm3 into Gm1. This is the answer. I hope this problem was also interesting. Let's see the next problem. Oh, this is another further interesting problem in OPAMP. See, this problem appears to be very tough, but it's one of the easiest problem you can think of. It's a very straightforward problem. This is R. So here you have a resistance of 3K and you have a voltage of 3 volt. Okay. I'm sorry, this is 1 volt. This is 1 volt. This current is I. So you have 3K, 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 12K, ground, correct? So what is given? Op amps are ideal. I equal to 0 ampere. What is R? Let us start solving. So the first important clue, what do we know? Solution. Let us start solving. Solution. Op amps are ideal, which implies R in equal to infinity. Okay. Then op amps are ideal, which means op amps in closed loop negative feedback mode, V inverting is equal to V non-inverting. These are most important points. This should immediately come to your mind whenever I am saying op amp is ideal. So now this is 0 volt, that means this will also be 0 volt. This is 0 volt, that means this will also be 0 volt. And this current is 0, this current is 0, this current is 0 because it's ideal op amp, this current is 0 because infinite input impedance. Now what is told to you? I is 0. I equal to 0, this is given. Now let us start. Now it is just going to be playing around with Ohm's law. Now this is 1 volt, this current is 0. That means this has to be 1 volt, otherwise current will flow, correct? So this is 1 volt, this is 1 volt, that is the only way the current can be 0. So this voltage has to be at 1 volt. Now this is 1 volt, this is 0. The current here will be 1 volt divided by 3K. Now this current cannot flow into the op amp, so it has to flow here. So this current will branch out like this. So this current will be 1 volt divided by 3K. So what will be this voltage? This voltage will be drop. So the current is flowing out. So this voltage will drop like this. So it will be 0 minus 1 volt by 3K into 3K. So this is minus 1 volt. So this is minus 1 volt. This is 0 volt. This is 3K. So the current will flow like this. Just Ohm's law. See, I'm just going to manipulate Ohm's law and Kirchhoff's current law. That's it. This is 0 volt. This is minus 1 volt. So effectively 1 volt. 1 volt by 3K will be the current that is flowing out. Now this current cannot come from the input terminal. So it will come from the feedback resistance like this. So this current is 1 volt divided by 3K. So what will be the V naught here? V naught is, this is 0. Current is flowing like this. So the current will be flowing from higher potential to lower potential. So this is at a higher potential. So V naught is 0 plus 1 volt by 3K into 12K, which is 4 volts. So this is 4 volts. This is 1 volt. This current is 0. If this, now let me write something. Let me call this as I1. Let me call this as I2. Let me call this as I. Let me call this node as some Y. At Y, by Kirchhoff's current law, what do we know? I1 plus I equal to I2, which implies I1 is equal to I2 since I equal to 0. This is given to you in the problem. This is given. Therefore, I1 is equal to I2. And what is I2? I2 is 1 volt divided by 3K. This is the current. And what is the delta V? Now what is I1? Look at I1. What is I1? What is I1? I1, this voltage is 4 volt. This voltage is 1 volt. So the drop is 3 volt. So 3 volt divided by R is I1. Correct. I1 equal to 3 volt divided by R, which is 1 volt divided by 3K, which means R equal to 3 volt by 1 volt into 3K, which is 9K. This is the solution. See, very simple. The moment I just applied the two principles, R in equal to infinity, because op amp is ideal. And op amps are ideal. So in ideal op amps in closed loop negative feedback mode, V inverting will be equal to V non-inverting. The moment I apply these two concepts, rest all is just a manipulation of Ohm's law, nothing more than Ohm's law. Ohm's law, Kirchhoff's current law. Ohm's law, Kirchhoff's current law. If you know to apply Ohm's law and Kirchhoff's current law, you can solve this problem. That's all you need to know. Clear? No need to remember any formula or mug up anything. It's very straightforward. Okay. Then next question, identify the type of feedback. So this is the question. This is R bias, R naught, or I naught. This is V bias. Correct. Identify the type of feedback. This is the question. So first let us solve. What is the input? What is the output here? What is the input? What is the output here? Tell me. What is the input? What is this circuit trying to do? What is this circuit trying to do? What is this circuit trying to do? Tell me. Yes, this is a constant current source. Where input is Vref and output is I naught. Because look at this. This is R. This R is fixed. Now look at this. This is V reference. So this is V reference. This is fixed. And what is given to you in the circuit? VCE, VB on is 0.7 volt and beta is large. Now what can I say? This is V reference. So this is fixed. V reference is fixed because of Zener diode. Vref is fixed. Why? Because of Zener diode. Zener diode acts as a voltage reference and it fixes this voltage. Now VBE is fixed. VBE is fixed, which implies VE is equal to VB minus VBE is fixed. So the emitter voltage is fixed. This is the emitter voltage. The base voltage is fixed, base emitter drop is fixed. So the emitter voltage gets fixed. Now R is fixed, VE is fixed, which implies IE equal to VE by R is fixed. It cannot change. And IC is equal to IE because beta is very large. Whenever I say beta is very large, what do I mean? Alpha equal to beta by 1 plus beta, which is approximately 1. That means IC by IE will be approximately 1, or implies IC is equal to IE. This is what I mean whenever saying beta is very large. Now look at this. Now IC is nothing but I naught. So I naught is fixed. Without even knowing what is my R naught, I am fixing my I naught. So that is the action of a constant current source. Correct? I naught is fixed without knowing I naught is fixed without knowing R naught, which is constant current source. Correct. So whatever may be the load, the current is fixed. The load may be anything, the current gets fixed. That's what is the meaning. Correct. So now let's look at this. So what is now, if I look at the signal picture here, small, let me look at this in the small signal picture. I have the BJT. I have the collector current beta IB. This is my collector load R naught, and this is my emitter resistance R. Now this is my VB, which is fixed. So this is your VBE and this is your VE. Now look at this. What is getting sampled? The load current, the load voltage. See here, this is the output voltage, correct? V naught. I am not sampling the output. What is the feedback element here? The feedback element is R. R is the feedback element. Now what is R sensing? Whatever the R is not sensing, R is not sensing V naught. But whatever is the current that is going to flow here, whatever is the current that is going to flow here, the entire current will flow through R and come back. So R sees the full load current, which means it is current sensing. Correct? And this current is converted as a voltage across R, and it becomes PE. And what is the amplifier? The amplifier, transistor is the amplifier, correct? BJT is the amplifier, and that is working on VB minus VE, which is VBE. So VBE is the motivational voltage which is driving the amplifier. And see, think about the negative feedback circuit. If you look at the negative feedback circuit, what happens? This is the feedback quantity, correct? The difference between the feedback quantity, the input and the different feedback quantity drives the open loop amplifier, correct? This is X, this is F. So X minus F is the input to the open loop amplifier G, correct? Similarly, you see here, VB is the input coming in, VE is the feedback quantity. So VB minus VE is the VBE, which is operating the transistor, correct? So it is clearly voltage mixing, correct? So clearly voltage mixing. So the type of feedback is V mix I sense. This is the type of feedback. Okay. So let us go to the last question. Last question is very, very interesting question. I'm sorry. This is 100 nanofarad. We have a switch. So beta is very large. VB on. is 0.7 volt. VCE sat is 0.7 volt. S was kept closed for long time and opened at t equal to 0. BJT will exit active region after dash millisecond. This is the question. So here lot of questions are getting, lot of beautiful concepts are going to get tested parallelly. So first, concept 1. Multiple concepts are involved in this problem. Let us look at the concept 1. Constant current charging of capacitor. What will happen? If I charge the capacitor with a constant current, what will happen? If I charge the capacitor, so look at this. I is equal to C dV by dt for a capacitor, correct? Now, I is constant. Now, C is constant, which implies dV by dt is I by C, which is constant, which implies V equal to dV equal to some constant into dt, which implies V equal to some kT. So this will be voltage will be a ramp. Please note, many people they get confused whenever they think of charging the capacitor, they think like this. This is not the case. This is the waveform of the capacitor when it is charged with constant voltage. Here I am charging with constant current. Correct. So therefore, constant current charging V ramps up across capacitor. If I do the other way around, constant current discharging, if I do, what will happen? V ramps down across capacitor. This is very, very important. Okay. This is a very, very important concept. Now let us look at the circuit. What is happening here? Many people they will get confused that for a NPN transistor I am applying a negative voltage, so the transistor will not turn on at all. That's a totally wrong concept. Here there is a negative 10 volt, which is more negative than this, so this will ensure that the transistor is turning on. So 0.7 volt is the VBE on. That means this voltage will be minus 5.7 volt. So this is minus 5.7. This is 10 volt. So the drop here is 4.3 volt. So 4.3 volt, 4.3K, 1 milliampere current will flow here. So 1 milliampere current is going, and beta is very large, so the same current will flow here also. So this is 1 milliampere. Now this 1 milliampere, this is 0.5 milliampere. So if I apply Kirchhoff's current law, this current has to be 0.5 milliampere constant. So now let us look at this. Yeah, it will be just one more minute, we will be done. Let's quickly look at this. So when switch S is closed, it is 0.5 milliampere. When switch S is opened, it will look like this, 0.5 milliampere. So this current is 1 milliampere. Just now we derived it. So this current will be 0.5 milliampere. Here the capacitor was parallel to a short, so the current was coming through the short circuit. But now the switch is opened, so the current will come through this. So the capacitor is discharged with a constant current of 0.5 milliampere, which implies V capacitor will ramp down, which means the voltage across the capacitor is the voltage at collector. Vc will ramp down. But Vc is at is 0.7 volt, which VE equal to VE is at minus 5.7 volt, which implies Vc cannot go below minus 5 volt. So when Vc reaches minus 5 volt, Q exits, Q is my BJT, okay? Q exits active region. So effectively we need to find the time taken. So time taken for capacitor to discharge by 5 volt. So what do we know? I equal to C dV by dt, which implies V equal to some I by C times T, correct, if I comma C are constants, which is what we are seeing. Current is constant, capacitor is constant. So therefore here T equal to V into C by I. V is 5 volt, C is 100 nanofarad, and I is 0.5 milliampere, which is nothing but 500 into 10 power minus 9 divided by 500. 0.5 milliampere is 500 micro, is 10 power minus 3 seconds, which is 1 millisecond. This is the solution. Okay, this is a very important problem in which you are looking at the saturation principle, active region, saturation region, operation of the transistor, what is VC sat, what is VB, what is the meaning of large beta, and what is the capacitor charging by a constant current and a constant voltage. All these concepts are tested in one single question. It's a very beautiful question. Okay, so I hope this session was clear and all the questions were clearly understood. Wish you all the best. Wish you all the best. Thank you. I hope the session was informative. Please join for more sessions. Thank you. Thank you.